Earth date 19th May 2021. Okay, so right. Before we start off with this week, let me give you the agenda of the next 3 days, right? So today is going to be more of we will explore the definitions of the differential and try to see how it actually relates to a certain thing like the functions and the vector spaces and all that. And once we have once we are a little comfortable with this today, tomorrow tomorrow we will look at we will revisit whatever we have done so far in a kind of like a summarizing chapter where I just give the intuition, right? I tell you how to look at the this thing the vector space, and I mean the tangent space, and the differential and all these elements. How do you look at them at from a purely intuitive viewpoint, right? So it all turns out everything it turns out everything has to do with really some form of like the Stokes theorem, and we will look into the details of that tomorrow, right? It will not tomorrow's session will not be Kobayashi strictly following Kobayashi no Mizu. There will be a lot of things that I will be introducing. There will be a lot of defense, right? Day after tomorrow we come back, or then the session after the next we will come back, and then we will try to revisit, we will try to set up some kind of uh, like propositions and go through some proofs. So it will be a more of what you see in the typical math courses. You will have propositions and you will have proofs, and that will develop your concept, right? As of coming back to today, today is looking at the right. So we had the differential. We left off at the definition of one form with the differential operator df is given by the summation of the f and with respect to ui, right, or uj. So now let us define the angle bracket, which is you have the angle bracket of the differential of a function at the point p with respect to x, which are the tangent which is the which is the coordinates of the tangent space at p, the local coordinates. You have the angle brackets is defined in such a way that you have x of f. So basically you are taking the derivative of this function here at this point, right? So x is the operator that is acting on f, and so you're basically looking at taking the derivative of x at the point p. Now moving on, so what is the one form? One form omega is we've visited the concept of a one form earlier, but let's go through another instance, right? So if u 1 to un is the basis of a local neighborhood, then du 1 to dun is the basis of the dual of the tangent space of that neighborhood, where the tangent space is given by the partial derivative with respect to u1 to un. So now one form omega written uniquely in the neighborhood of p is omega is equal to summation of j for whichever so summation of j fj duj, right? Fj is the component of w with with of omega with respect to u1 to un, right? So it is the dual of the function, the dual space of the function. So f, and then it can be represented in some kind of a column matrix, and then that is the elements of that matrix is given by uh, fj, right? Omega is differentiable if fj are differentiable. If fj is not differentiable, then omega obviously is not differentiable, right? Because like whenever you try to like act differentiable operator on whenever you try to operate something like on omega, then you need to differentiate f as well. If you can't differentiate f, you can't differentiate omega. Now let us try to understand this in a kind of let's try to understand the difference between the tangent space and the dual of the tangent space in some kind of an intuitive manner. This intuition is like kind of failing. I mean, it is only so limited because there is nothing concrete. It is just how I visualize it, and it will probably help if you can, take hints from this and try to get to your own form of visualization, right? So now you have a manifold M. Okay, these white circles are just manifolds. Okay, so you have a manifold M and there is a point P, and when you are trying to, obviously there is a local neighborhood around P. There is some sort of a local neighborhood around P. So if you have the local the neighborhood has the coordinates u1 to un, right? Now when you take a vector space or a tangent vector and act it upon this point P, so what you are necessarily doing is you are trying to like see how P changes, right? Obviously you will have some kind of a mapping, so that is why you have an atlas, right? If P is mapped to another point in the same manifold itself, right? If P is some sort of an internal transformation, that is possible as well, but it is also possible that this P is mapped to some other function on a different manifold. So you have M and M dash and P is mapped to M, and how how the P changes here versus how the P changes in the end is something that you really want to measure, right? So it is 2 points, and then you have a function between the 2 points, and how variation of function in the first point reflects in the variation in the second point is actually what you have to measure, right? So x is the coordinate basis here, I mean of the tangent space, and you have this you have this acting on the local neighborhood of P, right? You have the differential you have the partial derivative acting on the local neighborhood of P. Now f or the function is defined by the shape of the manifold and the symmetry, etc., etc. So it's basically either the atlas that so it is either defined in the atlas that you are talking about, or you can it is defined in the mapping with respect to another manifold, right? So now so now x is determined by the dimension or ui. So if you have if you have r coordinates, f is defined by the r basis, right? So now the dual of the tangent space is something. So if you are really acting your tangent space on a point, the dual is basically like the places that the point can move to after it is being acted, right? It is like if you are talking about you have a separate coordinate basis and then you are acting that on this, the dual is rather some kind of opposite, right? So intuitive idea is okay. So here in the tangent space, you are basically telling you, you need to give a function or some sort of like a way for the tangent space to act on the point, and that will tell you how the point will actually undergo some sort of a dragging or a deformation. But here in the dual space, or in the when it comes to the differential, you are talking about like this space. So you are defining some sort of space around that particular point where it has some sort of freedom to move. So here you are defining some like you are introducing a deformation, and you are like basically stretching this to some extent, and then you are talking about the magnitude of the stretching because of this the change in the local coordinates. But here you are giving it some room to stretch, right? You are saying that it has some room to stretch, and how it actually stretches is based on the function f. So f or the function actually determines how it really stretches or how it really deforms, where dui and the differential and the tangent space or the tangent vector tell you how it can deform in slightly different languages. All right. So given this, now you have okay. So given this kind of distinction between the tangent space and the dual of the tangent space, you actually notice that the idea behind both of them is somewhat same, but they are related to each other in a non-trivial way, right? So for example, like what I mean by non-trivial is, for example, like whenever you're thinking of some operation or some kind of like something is acting on something else or something is happening to something, right? Whenever you're thinking of some kind of mathematical notion of like change or operation or whatever it is, so you need to remember that it is not always trivial, right? So for example, the simplest example that I can give you is if you look at two matrices A and B, you take the dot product of A with respect to B, it is not equal to the dot product of B with respect to A, right? Under extremely except for under extremely special circumstances. So now if you look at this, if you try to understand how this dot product is not really the same, it is got to do with like the underlying definition of vectors and the dot products and that kind of make up the matrix, right? So this is the same way. So right now you have the derivative or the differentiation, or like you have that as an operator and you use it in two different ways. One is as the differential and the second is as the partial derivative of something. So when you use it in two different ways, it need not be symmetric. That means it need not tell you the same thing every single time, right? So so even though it represents the same idea, even though A dot B represents the dot product of two matrices and A represents the dot product of two matrices, understand that they both are not equivalent, right? So there is a slight there is a non-trivial nature to these kind of like operations, which even though they seem to be the reverse of the same product, same process, they don't necessarily need to have a converging or they don't necessarily need to give you the same thing at the end of the day, right? So when that non-trivial part of it like becomes slightly clear, right? It will take some time to sink in. Probably you can question why is this not so, why is there some sort of a difference in the way mathematical operators and objects behave. However, leaving you on with that question, now we move on to something else, right? We move on to the definition of one forms and an R forms and all that, right? So right, so a one form. So the dual to the tangent space Tm or T star m. T star m is the dual to Tm, right? So yeah, this is what dual means, right? Like earlier what I was talking about, like it looks like an inverse, but it is not really an inverse. Okay, there is a lot of semantic difference between a dual and inverse, and they are not the same, but the idea is somewhat similar. Like there is some process happening, there is some sort of a reversal of that process happening in some way. All right. So yeah, so that is what a dual essentially means. So now the dual to Tm or T star m or the one form. So T star m is called the one form. This is what we have defined. Ui is the one form, right? So the total one form or the like the one form defined at a particular point is the summation of all the corresponding duals of the function with respect to the one form, right. So you have a summation j f of j du j, right. So you have the dual of the function with respect to and then yeah, with respect and acting on each of the like the differential of the coordinate of the basis, right. So this is what one form is. Okay, so skip this, right. So now remember how we define the angle bracket. Now we are so if you take omega of x at a particular point, it means you are basically taking the angle bracket between omega of p and x of p. Now let's look at the angle brackets again, right. So df, this is your omega, summation of df at x of p is nothing but the x acting on the f, right. So you have omega, sorry, you have omega of x. So basically your omega of x is essentially you have taken the differentiation, right. This is a parameter, x is now just a parameter at the point p, right. So you have omega is equal to omega p x p, right. So this is for each x belonging to the module of the manifold, right, and p belonging to m. So now yeah, so this is essentially just say this is essentially saying that, so look, df of p x comma x of p is nothing but x of f. So as you can see, right. So now if lambda or wedge, this is called, this lambda looking lambda like character is called the wedge. If wedge of T star Pm is the exterior algebra over T star M, okay, and R form omega is an assignment of the element of degree R in wedge T star Pm to each point P of the manifold M. So essentially what this is you can define omega for any R form, not necessarily a one form, but any R form. And what is an R form? R form is basically when you take the wedge of two or more differential elements, right. So you have DUI or two or more one forms. So when you take the wedge of two or more one form, and yeah, so basically this is essentially if you have a function, yeah, so this is just some sort of notation. This greater than is just some sort of notation to indicate some sort of hierarchy whenever you are taking one form, some sort of permutation combination, that's it. But like essentially you are taking R one forms, and you have some sort of permutation combination of all those one form, and each of them has f, right. I mean has a corresponding function based on the function that is associated with the one form itself. We will look into how to get fi to I1 to IR in some future video. but this is essentially what it means to have an R form, right? R form is nothing but a wedge of several one forms, or like several two forms, or whatever it is you have. So this is what I is, right? So you have the wedge of like one form, and then you have wedge of two form, and then you have wedge of like so on. You have wedge of R form, right? So you have that is what gives you the summation. You take this wedge of all the one forms and their permutation combination, R2 form, I mean R by two forms and their permutation combination, so on, right? So this is what your R form, this is how your R form is defined as. So now a note on exterior algebra. Whenever I say an algebra, it relates to how one object interacts with another. What are the kind of like operations that can be performed on one object when you're talking about it with respect to another object. So an exterior algebra is basically defining a space outside the tangent of outside the manifold M, and your manifold can connect to the outside manifold, right? Like it can it's connect would be kind of like misleading word probably, but it's basically you can link two manifolds, right? You can link two manifolds using the exterior algebra, right? So essentially talks about how an n dimensional form acts on another m dimensional form to give an m plus n dimensional form. So this is what your exterior algebra means, right? It is proving, it is kind of providing a pathway for one manifold M which has n dimensions to leak into, or instead of talking about manifolds exactly, you can talk about the form, because the algebra acts on the form itself and not necessarily on the manifold itself, unless you have the n dimensional form. So if the manifold is of dimension n and you have an n dimensional form, and except for that particular case, you have an n dimensional form of a manifold of say r dimension, and you have an m dimensional form of a manifold of s dimensions, and both of them, so there is some kind of a flow or some kind of a linking between these two to give you a new m plus n dimensional form, right? This is very exciting, because it kind of gives you some room to escape and form something larger, right? There's some sort of poetic beauty to this. So you just have a flow outside, and then you kind of explore a whole new world, right? That is the poet in me speaking, but yeah, that's essentially something that happens, right? So so the intuition behind this whole m dimension n dimension is like an m plus n dimensional form is basically, if you have so if you have a basis for your n dimensional form, that is du wedge so and so d n dun. Okay, if you have a wedge product of all the forms, that is basically it is like talking about if you have u so if you have du1 here and du2 here, the wedge of these two gives you the area of the parallelogram here. So it kind of represents the net area of this, right? So it's two dimensions, right? So it's like you can talk about a sheet or something whenever you're talking about two forms, right? So when you're talking about a three form, it's a parallelepiped. So you have an n dimensional parallelepiped and you which are kind of orthogonal to each other, right? They are independent to each other. Now what if you take a new one dimensional form? So what if you wedge it with another one? So you have you have a two form here, okay, and then you wedge it with another one form that is pointing towards me. All right. So you have you wedge it with another one form. So you have like a parallelepiped here. So you have three vectors and then three vectors, and then you have some kind of a volume protrusion from these three vectors. That's the intuition, right? So you take n dimensions, you add n more dimensions, which are kind of like completely not really completely orthogonal to each other, but independent basis, right? That means you can have n like really orthogonal vector and n plus m orthogonal vectors in the new form that you're taking. So it need not be exactly orthogonal basis, because you can have a parallelepiped, or it need not be orthogonal vectors, but you need to have an m plus n dimensional or an m plus m dimensional form at the end of the day, which is like basically the volume of the new n plus m dimensional parallelepiped. So that is what forms are. We will go into more clear definition of what the wedge product or the wedge operator is in perhaps tomorrow's or the next video, where I will be introducing things. I will be giving intuition to most of the thing. Okay. So if you right. So what is an R form? It's a skew symmetric R linear mapping over the space of functions f of m of the f of m of like the module of the manifold cross product and time into the again the f of m, right? The space of function. So this is how you define it. Is basically what I told you, right? So you have x, which is you have some sort of like okay, you have some sort of a basis, or you have a coordinate basis, and then you like take some r combinations of the coordinate basis in different ways. So you have the differential, you have the one form, two form, so many times until you have r forms, and then you take the summation. So it's just another way of really telling you the summation that I explained, like omega. Yes, so I mean, instead of talking about one specific omega here, they consider the general space of this definition considers the general space of functions itself, or the space of forms itself. Right now, let's talk about omega. Let's talk about let's think about it in another way, right? The wedge product of r omegas or r1 forms is with respect to, so this is the coordinate r coordinate basis or r coordinate neighborhood, okay, is nothing but 1 by r factorial, the determinant of omega j time omega j of x of k. So x of k gives you some particular neighborhood. There are say r neighborhoods here, and then you take the permutation of each neighborhood with respect to each omega or each one form. So there is some sort of a linear permutation combination happening, and like so when you take it, when you take this sort of permutation combination, the thing so each omega j x k, or each like final this thing each final like each final one form at the basis of a neighborhood is given by is repeated r time, right? So it is I mean r factorial time. So this, if you look at this, it's basically telling you that if you take the wedge product in one particular fashion, you have a repetition of r factorial time when you take the determinant of this particular matrix, right. So when you represent all this in a matrix and you try to take the determinant of this, you have a scaling of r factorial time. Okay, so this is just what it is saying. It's an interesting observation, but it has to do with a more rigorous, if you try to explain the proof, it is basically you see all these combinations of omega k and sk that come into the expression of the determinant. So you obviously have so whenever you are taking the determinant, you are really taking the multiplication of each term and the subtraction. So you take multiplication and the subtraction to get the determinant, right. So in the end you have omega wedged r time. Okay, if it is an r by r matrix. Okay, so both omega and x have like r parameters or whatever. So you are really taking an r by r matrix and then you are trying to get the determinant of that, which is like you have omega repeated r times in the final expression. But if you look at it, there is so many repetitions because of the kind of because of the permutations and combinations that occur when you are trying to take j and k, that it ends up and you need to factorize it by, you need to factor it by r factorial time. Intuition, it's pretty intuitive, right. So you are looking at it r factorial times of permutation combinations. So whenever you are taking a determinant, you are really you need to factor it by r factorial, right. It occurs in a lot of places when you have some direct product or versus some sort of a determinant, right. So this is what your wedge on a basis x 1 to x r looks like. Okay. So now let's look at the definition of the differential. So a few simple differentials. So if you take all the forms to be of, if you take all the form r forms to be of a space dr of m, or simply written dr. Okay, so if you define that dr as the space, now dm is equal to d, which is the totality of all the r forms. So you have summation from r is equal to 0 to rn of dr of m, right. So now where your r0 is the space of function. So this is surprising, right. This is like you are including the functions or the kind of like mappings into the space of the differential itself, right, or into the space of the forms itself. So d0 of m is equal to f of m. So that is, so this is one of the really interesting ways to look about the relation. So if you, it's essentially saying that if there is some sort of way that I can go from dr to dr minus 1, so that is the same way that I can go from one forms, okay, to the set of the space of functions on the manifold M. So this is actually quite intriguing for a lot of reasons. So, and as I said, right, each new definition or each new thing that we are defining here really adds to the whole structure of this simple definition of open sets and then transformations regarding open sets. And each time you add some kind of a simple definition like this, okay, you are giving it very rich and interesting attributes, which we will see later. First, the first few days of differential geometry is just going to be talking about the different characteristics that you give the geometric whatever, right, the definitions and characteristics you give. And then the more definitions you build, the more characteristics you give, at some point you reach you reach somewhere where you can have a lot of interesting results from whatever you have defined so far. right? So that part, the exploratory part, will come soon, but right now we are going through the like the definition part of it, right? We're like trying to understand the rich texture of differential geometry. So yeah, so this is what so yeah, for this is function for a function f belonging to the function space and omega belonging to the uh, R this thing belonging to the space of R forms. So f omega is an R form defined as f omega of p is f of p omega p, right? So basically you have f acting on your one form f acting on your R form to give you the f of p at omega p, right? So it is basically you can write down both f and omega in the basis of the local in the local coordinates. So this is a pretty simple definition. So it is something similar to what happens earlier with the tangent vector, where you have f of f times a tangent vector, or f times x gives you f times x at the particular point p, right? So this is something similar that's happening here, right? So DEM, the space DEM forms an algebra over the real field. Another, so the emphasis is on the real field here. Real field, so if the manifold is of dimension m, the real field is of R m, right? So so it's like, so this is one more interesting thing, right? So it tells you a lot about how mappings on manifold can be easily related to the real field. So now talking about the properties of exterior differentiation or the exterior derivative D, right? So one, D is an R linear mapping of dm into itself such that d of the exterior derivative of dr is a subset of dr. So as I said, right, dm forms an algebra, and there is an algebra, and within that whole algebra, d or small d or the exterior derivative is mapping of dm to dm such that you have a kind of dimensional increment, right? So when you take the differential of d form of an R form, it becomes an R plus 1 form. So this is the first definition. The second is for a function f belonging to d0, df is the total differential. That is, so df is the total differential of this function, right? Simple. Now if you have omega belonging to omega as an R form and pi as an S form, then the wedge product of omega and pi, the differential of the wedge product of omega and pi is related to this, right? So d omega wedge pi plus minus 1 to the power of r. So this is basically flip between the positive and negative sign for the even and odd function. I mean even and odd like forms, right? So based on the rank of your form here, you have the sign associated to the second term, right? That is the omega wedge d pi. So this is basically acting like a chain rule itself. So but you have a negative sign here, and this negative sign here has to do with something that is quite interesting. It has to this negative sign has a lot of interesting implications, right? It has something to do with cohomology, Right. So it's quite fascinating, but it is rather based on some simple ideas that we will touch upon soon. The fourth property is that the square of the differential is 0. So this has to do with uh, the fact that boundary of a boundary vanishes. This will also be dealt with in the intuitive video. All right. So now so some more expressions of your forms in or the differential in local coordinate systems. You have omega as as I told earlier, right? You have an R form, you have this expression of the R form, right? Now your d omega is the differential of f times the R form. So you have, when you actually take the differential of f, you apply the rule number 3 here, okay, to take like each. So the differential is typically some product or some function with like the ui variables. So now you take the differential of this with respect to, you take the differential of take the differential of the function with respect to each of the I variables, and then you have you apply the chain rule here, and so it's split down into several different functions of the same form, right? So you have a class of you have a summation of several different R forms, R plus 1 forms. Okay. So d omega, if omega is an R form, because of this d here, so your d acts on each. So if f can be decomposed into omega, or instead of omega wedge pi, you can have omega into pi. So you can have this. So you will have a kind of like a chain rule here, and then finally you end up getting taking the summation of all the functions that occur in that way. So this is basically what the differential looks like with respect to the local coordinate system. Now let us look at a vector space. So it becomes important to define a vector space, because for each point, instead of just talking about functions, instead of just talking about particular mapping, we often need to allocate a vector space to the function itself. So when this happens, when you need to do this, these definitions, it becomes important to understand what a vector space is with respect to your R form, right? So a V valued R form. So V is the vector space. V is an m dimensional vector space. M is typically the same dimension of the manifold itself. Okay. So this is one important supposition you need to make. So M is the same dimension of the manifold itself. So V is an m dimensional vector space. We are defining it. Now a V valued. So there are some vector m dimensional vectors. There are m different values, an m by n matrix of values of a V valued R form omega on M is assigning a skew symmetric R linear mapping of the tangent space R time, the cross of the product of the tangent space R time into V. So you're basically mapping mapping T to P, T to V, right, for each point P belonging to M. So basically what you're doing here, okay, and less complicated words, is you're assigning, or of course you have a form on point P, you have an R form, and you're mapping this R form onto a vector space. So you're talking about, so basically what you can do is you can write your omega as a summation of the dot product of omega j e j. So your omega, okay, each each vector or each component of a vector can be taken as the dot product with respect to one component of the form. So this is basically this is an interesting result, right? So you have some sort of a direct mapping of your R form into an R dimensional or an M dimensional vector space. Obviously, when you when you're talking about an M dimensional vector space, the R form will be a subset of M, the vector space, right? So now omega can be written as the dot product between the the R form and the basis. E is the basis of this vector space. Now d omega, the differential, is defined as the summation of the differential of the form time taken the dot product with the basis of the space, right? So this is the definition. Of course, you can't have the differential with respect to the element of the vector space itself, but you can have the differential with respect to an R form. So given that, right, excuse me. So the differential at P of f, so we are now talking about functions and what exactly it means to take the differential of a function with respect to let's try to understand what it better means to take the differential of a mapping, right? So if you take a mapping f star of a tangent space Pm, tangent space Tpm into another manifold, okay. So this has T f of Pm. F of P is a mapping of from P to another point f of P on M dash, okay. So you have a mapping of f, you have a mapping f of one manifold M onto another manifold M dash, okay. So this is what like the differential looks like, right? So to understand this, let us visualize this, right? So this is how it actually works. So for each x belonging to the tangent space of M, choose the curve x of t in M such that x is the tangent vector at x t of to x t at p is equal to x of t naught. So remember earlier when we tried to define the tangent space, you take this parameter x t naught is equal to p and then you define the tangent space upon this. That is the same thing, right? So whenever a curve t whenever x is the tangent vector to a curve x of t at t naught, that it is the tangent vector at p, right? So p is equal to x t naught, right? It's a parameter. So now secondly, then f star of t is a vector tangent to the curve f of x of t at f of p is equal to f of x of t naught, right? So you're basically saying, hey, you know what, I'll take a point on the manifold and map it to another point, right? This is my f of p. So you're naming this new point q, which is given by the green dot. So your M, so basically your when you're taking this q and you're really mapping it to another tangent manifold or another manifold M dash, okay, you have several different ways you can take the map. So this f of p, like I mean this new branch, like you don't know what this real, like what this space is, like you don't know what exactly M is until you define M. So you can have several ways of taking and mapping P like this Q onto the new M dash, which is essentially you saying that you are taking P and transforming it and mapping it to M dash. So you are taking P here in this thing, and x of t act like f of P is giving you another point on a new manifold M dash, right. So how does this work, right? X of t is a curve, and if you use the if you use the neighborhood of u to, or like the local neighborhood, I mean if you use the local neighborhood u, the coordinates of that to differentiate it, this curve, okay, you will see that you will get a tangent here, right, at x of t naught. So this tangent, right, so understand. So now this tangent actually kind of deformed, and there is another function f of p which is also tangent to x of t at p is equal to t naught. Okay. So this is slightly complicated here, right. So you're basically you just need to remember this, right. So you are taking the parameter, and then because you have so this is at each point x of t naught. If you change your x of t, or like if you change your t naught, then you are changing your essentially the mapping to the new manifold, and yeah. So this is a kind of like complicated definition, but it just means that complicated the seeming definition, but it means that so you have so you can take the mapping f star of TPM onto T f of p m dash. So f of p gives you some sort of f of p gives you the mapping on M itself, whereas f star, okay, so more clearly f of p gives you the mapping on M itself, whereas your f star, let me write it down here. So your f star is all these mappings. Right. So f star is like all these mappings that you have. Okay. So mappings from M to M dash. Alright. So now given like there is some sort of a clearer understanding here, we can move on to define the dual of this function. Okay. So yeah, so one more property that you need to define is like basically if g is differentiable in the neighborhood of p, then f star of x times g is nothing but the x times g dot f. So you take the dot product of these two functions, and then you have the local, you differentiate it with respect to the local neighborhood, you get this, right. So this is essentially saying that you have f star at x, which is basically the mapping. So x f star at x, so you have x given by the local neighborhood, so you have f star, okay. F star is what decides which mapping of M to M dash happen. Just so f star is what decides what mapping of M to M dash is happening, and then you have neighbor. So yeah, So you have f star of x times g is nothing but the x times g of f, g dot f. Okay, so this is kind of fairly simple definition. Now we have decoded what it really means to talk about the tangent. I mean, there are so many terms here that it sometimes seems very complicated, but what you really need to understand is there is something happening like what I've shown you in this visualization, and then f star really fixes your function from the mapping from m to m dash. So that means it also fixes your mapping from the local coordinate system in M to a new coordinate to new coordinates in M dash. So it's just a mapping. Now for an R form omega prime on M prime, the R form f star of omega, this is the upper star, right? So f raised star omega prime on M is the transpose of f star, right? So you can write down this transpose as f star omega prime of x1 to xr is omega prime f star of x1 to xr. So it's basically you are, instead of writing down, so you are kind of like you can write down the function with respect to each of the coordinates. So you can actually multiply the function with respect to each of the coordinates, right? So you can take the function action on each of the coordinate and modify it in some way, and this is hey. Now d commutes with f star. So if you have d, the differential f star omega prime is equal to f star d omega prime. Okay. So now the last definition for today is if your f is the mapping from M to M prime of rank R is of rank R at P is belongs to M, then like if the f star of the tangent space of M is the R, so the dimension, so it just like related to the dimensions of your function and your like star or the star function. So this is really the local, like, so let me go back here. I think this wasn't clarified. So you only need to use f star when you're really when you need to define P. If your f is general or you don't need to define P, or like f is same for all the P, okay, then you use just f. But if it is more specific, so f star means, okay, please define P. So a star here at the bottom is telling you please define the neighborhood. That's all it is. So when you define the neighborhood, so you have all these like this is more of a notational result than anything really intuitive, this last section. But the key to today's understanding was what what the f star actually means, like in terms of like what it means to kind of like define the connection between two manifolds. And then we also had the discussion of mapping of the differential or the forms onto a vector space, and we also discussed what the exterior algebra looks like. So we will be this needs a lot more clarification, because this is the kind of proofs and the kind of structure and the kind of beauty that is represented by this whole exterior algebra is just like, it's very interesting, and this definitely needs a lot more intuition, and we will do that soon enough. Then we also had this discussion of your space of R forms, and yeah, so and the algebra of your R form, right? So then you also, so we started this discussion with the difference between the differential and like a little more clarity on the definition of a form of one form, and then we discussed the definition difference between the tangent space and the the one form or the R form, right? So with that we conclude today's discussion. Hope that was enriching, and so a few more discussions like this, and I think we will be done with the definition part of it. So from here there is only so once you have like defined more or less everything, right, there are still a little more complicated definitions that will obviously come along the way, but once we are done with the basic kind of definition, hopefully we will like come across more interesting results and proofs soon enough. That is like we get an opportunity to really look at how all this is kind of non-trivial, and where exactly does it show up, where exactly does it act, and then what are the kind of identities and distinctive properties that you can have from these basic definitions. So there will be there will be few more there will be a lot more definitions coming up, but then soon it will take on to a more like discussion on the results and the kind of theorems that you have. So with that we end today. See you the next time around. Bye bye.